15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on this, the 287th episode of Space Nuts. My name's Andrew Dunkley, your host. We talk astronomy, space science, just about anything that people desire, and we get lots of good ideas to discuss from the audience, so thank you for that. Today on the program, we are going to be doing shock, horror, a James Webb Telescope update. Although we're getting a lot of questions about it too, so it's obviously at front of mind at the moment. We're also going to talk about what drives cyclones on Jupiter, and you might be a bit surprised by the answer to that question. And it is thought that there used to be rings around the sun, and that makes me wonder what happened to them. And it also may have resulted in Earth being smaller than it could have been, perhaps. And that cube that the Chinese found on Mars, they've finally figured out what it is. It's a real big surprise. Not. Plus some audience questions from James in Cincinnati, go the Bengals, Ralph in Northern California, and Andy in Eastbourne. That's all to come on Space Nuts. My partner in crime is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How did you know I was a criminal?
I saw your mugshot.
Yes, that's right. Forward and sideways, that's right.
It's all over Facebook.
Oh, yes.
Yeah. How you been?
Very well, thank you. All good. One slight downer in the Watson family is my younger son, Will, who is now 20... be coming up to 26 this year. He's got COVID and he's not very well. Yeah, he's languishing, feeling really crook at the moment, and having to isolate. And he lives actually in Newcastle, where you used to
my stomping ground as a kid. Yeah,
Indeed.
Well, we know many people who've got it now. It's reached that point where it's not a matter of if you're going to get it; it's when.
No,
and
exactly.
We're just pressing on regardless. But I know of half a dozen people in my immediate circle that have got it. So far, so good for me and Jude. But it can't be long. She had 2 staff members out with it. One of the staff members I work with, the Salvation Army office, her husband's got it. Yeah, it's we've been dodging bullets like no one else's business, but you can't dodge them forever, I reckon. But the good news is I got my booster yesterday, so that's done. Yes. Yeah. No side effects either. Oh, maybe just a little bit of fatigue, but nothing significant. Got the Pfizer dose this time because I got AstraZeneca the first time. So
that's the same with me. That's exactly what happened. And I had no side effects either from any of them, in fact. I've been very lucky.
I got to tell you, though, they released a study, a month or so ago, to say that they've discovered that AstraZeneca is the vaccine that keeps more people out of hospital than the others.
There you go.
Oh, dear. Anyway, I'm happy to get anything. So...
Yes,
that's where I'm at. Enough of COVID. I think we've spent 2 years talking about that, and it's not over yet. But let's get on to our first topic, Fred, and that is the latest update on the James Webb Telescope. I saw some recent reports to say that all is going well. Things are unfolding and unfurling, and it's going along nicely. I've seen some great astrophotography too. A few people have actually picked up images of it, which is quite astounding.
Okay, no, I haven't seen that. Do they have any detail?
No, it's just a streak of light.
Yeah. That's what you'd expect. It's not big enough really for a small telescope to resolve it into a shape. You can do that with the International Space Station, but of course that's only 400 kilometers away. So anyway, you're right. The news is all good coming out of the Space Telescope. Sorry, the James Webb Space Telescope. The big news, of course, is that everything that was supposed to unfurl has done. And the latest thing was the last portion of the mirror. Remember, it's in 18 segments, but it basically was in 3 parts with a central section and of I think 12 segments, and then 2 3-segment sectors on the outside that unfolded and locked into shape. Of course, they still haven't turned that array of mirror segments into a contiguous optical surface yet. That's for the future. They've got another almost 6 months before we expect, in fact, more like 5 months before we expect to see any images from it. So there's a long way to go still. But the telescope is in good shape. There was a really nice comment from Thomas Zurbuchen, who's chief of NASA's science missions. He said, "We have deployed the telescope on orbit, a magnificent telescope the likes of which the world has never seen." He was talking to the team that did it, and he said to them, "So how does it feel to make history, everybody? You just did it." I love that. Yeah. And it is. It's a big step, and it's fantastic news. The telescope is well over halfway to its Lagrange point. It's more than 1 million kilometers away. It's probably significantly more than that now. That was where it was a couple of days ago. So really, very, very, very good. Very good news coming out of the Webb. And let's keep our fingers crossed that all will continue to do well.
How quickly do signals and instructions to and from the James Webb Telescope take once it's reached its destination? It wouldn't be that long, would it?
It's not that. No, it's not. 1.5 million kilometers divide by 300,000. That's an easy calculation. It's got a 5 in it somewhere in the answer. So 300,000, is it 50 seconds? That might be right.
I'll take your word for it.
No, it can't be 50. It's 5 seconds. That's the answer.
I'm just doing it now.
Thank you.
There you go.
Yes, it's 5 seconds.
Nice work. Well, that's good, isn't it? Yeah.
Yeah.
I did hear a news report only this morning that they reckon it's got enough fuel to work for 20 years.
Yeah, that's right. Keeping it on station, principally.
Yes, exactly. Okay, well, we'll probably have another update for you next week. I think the scariest part's over, but there's still a bit to do, so don't count any chickens as yet.
No, that's right. There's always the unexpected.
Yep.
Yeah. In fact, they've already experienced the unexpected when I think we might have mentioned this last week, Andrew, that the overheating motors, yes, when they stretched the heat shield or the sun shield. Anyway, that all got cured by taking them out of the sunlight, and it's all
indeed.
Fixed.
Okay, let's move on to our next story, and this is one that has been published, a new study into what might be driving the cyclones on Jupiter. For those who have no idea what I'm talking about, some people call them typhoons, some people call them hurricanes.
Yes.
We call them cyclones in Australia. And it's an interesting development in terms of what they've come up with, because what drives cyclones and typhoons and hurricanes on Earth is the oceans. There are no oceans on Jupiter, but they think it's pretty much the same kind of thing.
Yes, that's right. It is. It's an amazing story, this, and I guess to some extent you could lead your thinking in this direction simply by looking at some of the photographs or some of the images that of Jupiter's cloud belts that have come back from the Juno spacecraft, because that's what's really driven this realization. Juno, NASA spacecraft in orbit around Jupiter, in an orbit that actually carries it within Jupiter's radiation belts briefly, which meant that all the electronics had to be specially shielded. But Juno's been doing a fabulous job. I can't remember when it went into orbit. It's a few years ago now. But the images that come back show the structure in these cyclones. You know, the structure around the Great Red Spot, which itself is a cyclone, but other smaller features. And in particular, the way you can see the way these circulate, these spinning fragments of atmosphere with their different coloration, how they sort of drag the other atmospheric features around with them and cause these eddies around the edges of them. And it was as you said, oceanography. It was a physical oceanographer by the name of Leah Siegelman, who is at the Scripps Institution for Oceanography, well-known oceanography institution at the University of California, San Diego. And Leah looked at this and thought, wait a minute, this atmosphere is behaving like an ocean. And, you know, it's basically what she's done is looked at the images in close detail and bringing to bear the physical principles that are used in what's called geophysical fluid dynamics, the way fluids work on the Earth. And basically has come up with evidence for something called moist convection as being the driving force for these phenomena. Moist convection is essentially when hot air rises. It's convection. That's exactly what it is. It's warmer air rising, but of course there's moisture in it as well. And there's a nice quote from Leah. She says, "When I saw the richness of the turbulence around the Jovian cyclones, with all the filaments and smaller eddies, it reminded me of the turbulence you see in the ocean around eddies. They are especially evident on high-resolution satellite images of plankton blooms, for example." So, you know, we've got images that look similar, but caused by an entirely different, not entirely different physical process, but entirely different phenomena that reveal the images. It's the coloration of the eddies caused by different materials within Jupiter's atmosphere that gives you the impression of these things on Jupiter, and plankton blooms on the Earth. But what's driving them, the underlying physical mechanisms, are common. And in fact, it's got it's got some neat outcomes, because we understand the Earth's ocean better than we understand the atmosphere of Jupiter. And you might be able to draw conclusions from the way the Earth's ocean behaves, and actually test that on the atmosphere of Jupiter, whether you've got similar phenomena. As she says, once again, this is Leah, to be able to study a planet that is so far away and find physics that apply there is fascinating. It begs the question, do these processes also hold true for our own blue dot? So you can do it both ways. You can look at, you know, the phenomena on Jupiter and draw conclusions for that and say, does this work on Earth? So a very nice piece of work. Very nice indeed. For
sure. And in answer to your question, the Juno space probe went into orbit around Jupiter in July of 2016, the 4th of July.
Yeah, it's amazing. So it's, 5.5 years already. Feels like a couple of weeks.
What was the length of that mission supposed to be? Do we know?
Yes, it was very well planned. Actually, I think they're still on schedule with it. I do remember that looking at the mission profile, because I think as the mission goes further on, they get the orbit changes. There's a lot of orbit changes for the spacecraft, and they probably take the higher risk things like plunging deeper into Jupiter's magnetosphere later in the mission, when you've got some good data from the beginning. A bit like Cassini, which flew between Saturn's rings and the planet right at the end of its mission.
They took a big punt, and you know, if it all came to nothing, well, you know, we got what we wanted.
Well, that's right. So, yes, I'm not sure of the answer to that, but we can certainly check up and find out. But I do remember it was very well, you know, is well documented what was going to happen.
Yeah, I think I've said before, it must be exciting to be on one of these mission teams. Juno got a lot of attention when it first started, and what was it, 5 years it took to get there or something? And, you know, these people are still working. they're still, it's not a matter of, okay, it's got there and it's going around taking pretty pictures. People are still working the project. And it'll be the same with James Webb. It'll be the same, any kind of mission like that. There are control rooms all over the place where people turn up every day to do what they need to do to get the data and learn everything they possibly can about these strange worlds that we're so close to on a universal scale.
What a job. And for many people, that's a lifetime's work because they're probably involved with the mission planning, 10, 20 years before the mission flies. I remember talking to Linda Spilker, who was the project scientist for Cassini. She came out to Australia a couple of years ago, and we looked after her here because she gave a lecture for us, the Alison Levick lecture. And she said it was her entire career, basically. And she's a very mature scientist. She's not, she's still working and still doing great stuff, but she's not in her 20s anymore, if I can put it that way, and neither am I. And she said it's her entire career, and she's still going strong with possible future missions to Saturn. Wow. So long may it continue.
Yes, indeed. Fantastic. All right. We will obviously, there might be more to tell in regard to the Juno mission.
Yeah, I think so.
Going forward too.
Indeed.
And you'll hear it probably first or 50th here on Space Nuts. Oh dear. We'll take a break. You're with Andrew Dunkley and Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, if you're a social media follower, we are on social media, and we have thousands of people that are following us on Facebook, whether it's the official Space Nuts Facebook page or the user-created Facebook page, which is the Space Nuts Podcast Group Facebook page, where you can all talk to each other, ask each other questions, upload your pictures. A lot of people do that. Sandy in Melbourne has been publishing a lot of his astro photographs, and I've got to send Sandy a shout out and a thank you because he's been helping me with this little baby here to get my astrophotography kick-started. So I really do appreciate what he's been doing. So thanks, Sandy. But yes, if you would like to get onto social media and find us, you can do a search in your Facebook search engine for Space Nuts or Space Nuts Podcast Group. We're also on Instagram. Spacenuts.io is our username, and our numbers are pushing on towards about 200 followers now. So it's growing really fast. And we appreciate that. Yes, thank you for chasing us up or following us on Facebook. And we occasionally get questions through social media as well. And that's lovely. Now, Fred, what's this thing about Earth being smaller than it could have been because there may have been rings around the sun that stopped a super Earth from being born? This is very, very strange. And I'm guessing we're talking pre-planets, the very, very early stages of the solar system.
We are, yes. So we're talking about the time when the sun was a newborn star. It was surrounded by a protoplanetary disk, which is a disk of dust and gas, which is very turbulent and in which the planets form. And we know these things exist, or we know that the sun had one of these disks around it because we see them around other stars, around young stars. And as I said, they're called protoplanetary disks. But there's interesting details in this. Now, when we know much more about the origin of the solar system by looking at the way other solar systems have evolved. And now we've got this almost an industry of discovering the planets of other stars. We can look at these distant solar systems and compare them with our own. And that is the basis of this work, which has been carried out by scientists, one of whom at least is at Rice University, which is in Houston, in Texas. Actually, I think he is the lead author, Andre Isidoro. And what they posed the question. In fact, I can quote Andre exactly on this. It's always nice to be able to quote these scientists, saying what they've actually said. He says, if super Earths are super common, because that's what we found pretty well in our investigations of other solar systems. If super Earths are super common, why don't we have one in the solar system? And that's a brilliant question. You know, if other solar systems frequently have these planets which are about twice the size, the diameter of the Earth, up to 10 times the mass of the Earth, what we call a super Earth. If they are as common as they seem to be, why haven't we got one? What we've got is, of course, the ice giants, Neptune and Uranus, which are rather bigger than that. They're not what you'd call super, you know, you wouldn't call them super Earths. They're too big, and they were formed out in the depths of the solar system, whereas the rocky planets were all formed in the inner region of the solar system. And that's actually the clue to why the solar system doesn't have one of these, that Andre Isidoro and his team have actually uncovered. So they've done all kinds of modeling of what the early solar system was like. And it comes down to something that I think you and I have spoken about before. I certainly wrote about this in Spacewalk because it's such an interesting idea. The idea of these frost lines, or sometimes called snow lines, which is where the distance from a star, where, for example, where water turns from a vapor into ice, basically, that will be called a water snow line. So there's, and actually, the neat thing is the water snow line is, if I remember rightly, it's somewhere between the orbits of Mars and Jupiter today. But it may not have been like that in the early solar system. I think these things were closer in the early solar system. Anyway, you don't just have water that produces a snow line. Further out, there is a carbon monoxide snow line where carbon monoxide becomes an ice rather than a vapor. Excuse me. Carbon monoxide, of course, found in comets. Comets are made of ices, and CO ice is one of them. But there's also further in towards the sun, where the temperature is hotter, and certainly in the young sun's period it was. I think I've got that the wrong way around. Actually, I think the young sun was cooler than the present day sun, which is why these lines are closer in to the sun rather than further out. Sorry for the confusion there. But anyway, further in, when you get nearer to the young sun, you come to a line which you could still call a snow line, but it's kind of not really anything to do with snow. This is where the silicates, where the rocky stuff actually turns into a solid material rather than being a vapor. And it's sometimes called the silicate sublimation line. Sublimation is when something turns from a solid into a gas. And so if you go nearer than that, you've got a gas. The silicate's a gas rather than solid. So what you've got is all these regions where there's this key transition from a vapor to a solid for different materials. And it turns out that you get planetesimals forming in those regions. These are the things that are the rudimentary building blocks of planets. And the theory that these people, this group at Rice University, have developed is that because you've got these regions where the planetesimals are more common, you get essentially what they call pressure bumps. Regions where the dust and material is concentrated, and that actually itself generates the planetesimals because of the sublimation features. So what Dr. Isidoro says is our model shows pressure bumps can concentrate dust, and moving pressure bumps can act as planetesimal factories. So, the two go together. The pressure bumps regulated how much material was available to form planets in the inner solar system. And so what they're suggesting is that it's this regulatory attribute of the pressure bumps that stops the Earth turning into a super Earth. I'm not really explaining this very well. They said if they it's basically the way these rings form dictate what size planets you get. And they suggest that this comes from their computer simulations, that if at least one of these rings of planetesimals was delayed, if it formed later in the solar system's history, then you might have got super Earths rather than just standard Earths. Dr. Isidoro made a comment. By the time the pressure bump formed in those cases, this is the sort of inner planet region of the solar system. By the time the pressure bump formed in those cases, a lot of mass had already invaded the inner system and was available to make super Earths. So by the time when this middle pressure bump formed might be a key aspect of the solar system. In other words, had that been delayed, the super Earths might, because there was mass available to make super Earths, had that pressure bump been delayed in its formation, you might have got super Earths, but you didn't because it wasn't delayed. I'm sorry, I haven't really explained that very well.
It all came down to the timing.
It's the timing, that's right, exactly so. But a really interesting study, and one, for any listeners who want to follow it up, there's plenty of detail on the web.
It's in Nature Astronomy, I think.
That's where it's published. That's right. I've been looking at the Science Alert page, which is always worth a look. It's a good news site.
All right. Here's a question for you then. Let's assume for a moment that the conditions and timing were right to create a super Earth, and that this planet became a super Earth in its early days. What would that have meant for us?
Yeah, we'd have been super Earthlings. So rather than just standard Earthlings, we'd have been super.
In what way?
I don't know. Well, we might have been, this is a bigger planet we're talking about, 10 times the mass of the Earth, significantly greater gravitational pull. Who knows how we might have evolved, but it could have had life evolved and developed to the stage that it has now on planet Earth. Who knows what we might have been like? We would certainly have been very different.
Bigger?
I think we'd have been bigger. We'd have had to be beefier with solid, big boned. Have been big boned. That's the
not
word.
bad. I'm just big boned.
Yeah, because you'd have needed the strength of those bones to, put up with the increased gravity. So your bones might have been made of something else other than calcium and things of that sort.
It's interesting to think about, isn't it?
It is, yes. There's a science fiction story.
There probably is. There probably is. Although in the Turanian Enigma, there is a species that have those kinds of characteristics.
Big boned.
Yeah. Yes, but for a different reason. But, I went that way.
Yeah.
Maybe I should have thought of a super Earth, but anyway, doesn't matter. I'll save that up for another one, another story one day. Yeah. No, but it's fascinating. So we are what we are because of just the freak of timing.
Maybe that's right. Yes, maybe that's right.
Fascinating. All right, that is where we'll leave the sun and its rings and the not super Earth that we live on, and move over to the greatest mystery in human history, and that is the cube that they found on the moon when the Chinese U-2 rover sort of pointed its camera and went, "Oh, look, it's a box." They've found out what it is, Fred. I'm very excited to learn the answer to this question. As you can see, I am just over the moon.
Yeah. You should be on the radio. It's a rock.
Of course it's a rock. What else was it going to be?
It's always a rock, isn't it? I mean, it's the age-old issue of pareidolia, where we see things that look like something else. And, of course, Mars has been the place where most of these things have come from. I made a list a few years ago for a talk of all the different things that have been seen on Mars, from witches' hats to top hats, truck tires. There was a truck tire found on Mars. There's a grey ghostly lady who never seems to move. She's been found on Mars, but they're all rocks.
It's funny. What's it called? Pareidolia? Is that what you said?
Yeah,
where you try to create. You see something and you give it a life image, if you like.
Yes, we make it into something that's familiar.
that happened to me this morning. I was on the way to the radio station before my breakfast shift, and the sun was already coming up, so there was a bit of light. And I saw something ahead of me, and I thought, oh, that's a dead rat. For sure. No, it was just a piece of tyre rubber. But my brain interpreted a dead rat.
Yeah, that's right. I've swerved for dark patches, just, a bit of dark bitumen on the road that you think is a kangaroo. Yeah. It's exactly the same thing.
Yeah, you don't want to hit one of those things. They are,
no.
Speaking of big bones, you do not want to hit a kangaroo.
No, exactly. Many times I've had accidents like that, which are always very, very distressing for everybody concerned.
They certainly can destroy a car. And
indeed, yeah.
All right.
So anyway, nothing like that on the moon, and not even a cube. Actually, the Chinese people commentating on it in China, they nicknamed it the Mystery Hut. They thought it looked like a bit of a house or an enclosure. Right. But in fact, the pareidolia has continued because what they did was take the rover, which is called U2. It's U2-2, actually, this one, because U2-1 was on the near side of the moon, and U2 is the jade rabbit. That's what its name means in Chinese in China. But the first person to see this rock in a bit more detail apparently thought it looked like a jade rabbit. It's a rabbit.
Oh no!
It says that it's the Chinese Aerospace website has a journal on driving, a driving diary for U2 number 2, and one of the comments is the drivers were a little disappointed that this was a rock, but just as everyone was lost, the driver stared at the enlarged picture and covered his mouth and exclaimed, "Gosh, this is U2." So it's now, the rock is being called Jade Rabbit because that's what U2 means.
Well, I had two theories. It was going to be a rock, or it was going to be my missing Amazon delivery. So. But that's okay, because Jeff offered to go and get it for me.
Good on you, Jeff. Yeah.
All right, but it's just a rock. So very disappointing.
It's just a rock.
As they all turn out to be. This is Space Nuts with Andrew Dunkley and Fred Watson.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.